We have already talked about DA fits, that is the influence of a point when we are trying to predict the y value of that same point itself. So for that we have deleted that case and then tried to predict the y value of that point based on the remaining n minus 1 points. Now one problem with this is that when we are working with n points, we might be interested in other things also. That is, you drop the third point, you want to know how that influences the prediction for the 10th point. In this case, we dropped the third point and we became interested in how the prediction of y value for the third point itself was affected. Now, if we want to take all these cross terms also, then there are too many of them. There are n square many of them, and it is difficult to summarize them. Now, Cook's distance is a way of doing that summarization, and it is defined in this way. Cook's distance di stands for, so here I is the particular case that you are deleting. Cook's distance for that is the following. You try to predict all the things using the entire data, that is your yj hat. Now you drop that ith case and again you try to predict all the things, that is your yj hat I. You take the L2 norm between them. So you take y hat, the entire y hat based on the entire data and also the entire y hat without using the ith case. But you are still predicting everything including the ith case. Take the L2 norm, that is the numerator, and standardize it by dividing it with p plus 1 into sigma square hat. Remember, when you are using sigma square hat, you are using the full estimator. That's how Cook's distance is defined. I am not entirely sure why you are not using sigma square hat I. Possibly this will give you certain better mathematical properties or something like that. I do not know. And this p plus 1 basically is the total number of columns in X. So p many regressors plus there is one intercept term. So if you do not have the intercept term, you drop the 1. And remember, this is not really for the ANOVA setup. This is for the multiple regression setup. All the things are continuous. Then the di's give you one particular vector, or you want it to up to dn, and that is what was printed. So naturally, if any of these quantities is large, then you suspect that that has a strong influence on the quality of the fit. Okay, so now that we know what is meant by Cook's distance, you can see that this is the list of these. Now, they also print the head values, namely the diagonal entries of the hat matrix. Now, based on all these things, somehow you have to draw a conclusion. So, which are the influential cases? Now, they have various cutoff values for that. And these cutoff values are based on some heuristic, some asymptotic Gaussian distribution, etc. I'm not going to go into all those cutoff values. Something is, you take the total number of regressors divided by that n. If it is exceeds 3 times that, then you consider that as significant, and this is a rule of thumb, etc., etc. If you want, you can take a look at Wellesley-Poo and Wells, and they give you all those cutoff values with some justifications. But here they will give you directly the conclusion. They have added one column called inf, that is whether it is influential or not. If they put a star, that means it is an influential point. So Chile, I think, is one influential case. Now how they have decided, that depends on some composite thing. So they have used df beta A, they have used Cobb ratio, they have used this and that, and finally they say Chile is one thing that requires a second look. And then you have got United States is another one. Then you have got Zambia and you have got Libya. So these 4 cases requires a second look. Possibly these are influential observations. These are influential observations. So you should make sure that they are not ruining your fit too much. They should really be in your data. There is no typo for them. So you should look at those things. Now this is kind of a blind approach. So they computed lots of numbers and finally somehow they gave you this thing. But most likely you will not be satisfied with that. You would want to take a look at the individual things. So for that, what I have done is you can extract the various quantities. For example, you can extract the R student values. So the function R student will do that. So let's just do that extraction, and you might plot it with that AB line 0, and you can try to find out what the things are. So let's do the plotting, and when you see this plot, you naturally want to know what this point is. That looks like an outlier. So R student will really not tell you whether it is an influential point or not. It will tell you whether it is an outlier or not. This is an outlier. Here is yet another one. Now you will be interested in knowing exactly what country does this correspond to. There is a function in R which will enable you to do that. That is called identify. So it is very much like the function locator, which we have already talked about, except that it will also label. So you write identify, then the value that you have plotted, then you also provide a label. In this case, I provide as labels the row names of my data set, namely the names of the countries. So the moment I do that, I execute that, nothing apparently happens. You go to the plot and you will see that your cursor has changed to a plus sign, much like locator. It is calling locator internally, and then you take your cursor to that point and left click, and you will see the name Zambia. So that is Zambia, which was indeed identified as one of the influential things. You saw that we had star against Zambia. Now let's look at this fellow, and this is Chile. Now observe that all the other three things that it also got us, what for us, three, or I think, not three, I think it discovered how many for us. Let's just see. It discovered 4 influential points for us. Out of them, only 2 are actually outliers. So the remaining things are really not outliers. So they are inside this. So merely by looking at the residual plot, you will not be able to understand that there are 2 others which are also potential problem points. So you can do this for all the things. Now what I will do is I will just convert this. I want to come out of this. It is tilde plus. So I will just do a right click, and then I will come out of this identify loop. And now this is quite useful. So I will write a little function which is called checkpoint. I just call it checkpoint. What it does is it first makes a plot, and then it also calls identify with that suitable label. So I will just load that function. So I've loaded the function, and then I can just call checkpoint rs directly, and it will do the job. Now let's take a look at the head values. Now it is commonly considered that if some head value is large, that requires a second loop. So let's just take a look at that head values. So what I will do, I will again go there. Automatically identify has been called. So this fellow seems to be pretty off. Libya. And this fellow seems to be weird also. United States. This thing, let's take Japan. What is this? Ireland. Okay. So Ireland was also not too bad, but something that is not like the bulk of the data. So maybe you should take a closer look at that. I right click and come out of it. Okay, now let's take a look at the fits. Same story. So in this case, I am just looking at each one of them individually so that you get a better idea. So these are my DF fits. So how they influence the fit. So this one is an influential observation so far as fit goes. Japan. This one, Zambia. So these were already reported when I looked at my influential values. Ireland was really not reported because it was not that influential. It was more or less close to the bulk of the data. So this is how you carry out this influence analysis. But above all, you should remember that all that it does is it just draws your attention to certain values which are potentially dangerous. Now you should take closer look whether there's typo, domain knowledge, etc., and then carry this on.